Hello, in today's lesson, I'll be showing how to model the eigenmodes of a sphere using COMSOL 4.3. Now, since I'll be modeling the eigenmodes of a sphere with diameter 1 meter, I'll want to choose a 2D axisymmetric, since a sphere is a nice axisymmetric object. I'll hit next. I'll be choosing structural mechanics as my physics and solid mechanics. I'll add it, and you can see here the dependent variables that it will solve for. We hit next. I'll want to do an eigenfrequency study, and I'll hit finish. Now, since it's a 2D axisymmetric object, we see here the axis of symmetry, which is the r equals 0, indicated by this red line here. I'll need to draw the geometry, but only the part of the geometry that will be revolved around the axis. So you can import any object that you wish, but you can also build your geometry. So by right clicking on it, you'll see a set of primitive objects, and I'll be selecting a circle, and the radius will be 1/2 meter with the center at 0, 0. So I'll build that. There it is. And I'm going to also build a square with a side length of 1 meter, and I'll want it to build that starting at the corner of -1 and -0.5, and I'll help build that. I'm sorry, not -0.1 but -1. Alright, there we go. You can hit the zoom extents button to see it a little bit better, and I'll be wanting to take the difference of those two objects, so you can do a Boolean operation, difference, and for my first I'll add the circle, and from the circle I'll want to subtract the square, so I'll add it. And to see the difference, you hit build selected, and there it is. You hit zoom extents again to get it into view, and that's the object that we want to rotate around the axisymmetric. So now moving on, we'll choose copper as our material. So if I right click on the material and choose open material browser, you see there's a built-in library. Under built-in, there's a set of materials. I'll want to choose copper, and I'll add it to my model. You see it already selects the domain 1, and you'll want to check to see that the ones indicated either by green check mark or red cross are filled in. So if it has a red cross, it means you need to fill in the missing values. But we see here that there's green check marks for the density, Young's modulus, and Poisson's ratio. So it's all COMSOL will be happy when we solve for it. Now, under the physics of solid mechanics, we see here two different color schemes. So if we right click on the solid mechanics, we see the top here, we see this kind of the solid filled in white objects on the left hand side here. These are volume forces, or body forces. And you hit more, you can see more conditions on the body of it. Now if you want to add a constraint or some type of condition on the boundaries, we see here with the little kind of magenta sliver, these are all meant for boundary conditions. And if you go under points, you can also add point constraints as well. Now, since we are finding only the eigenfrequencies, you don't need to add boundary forces to your object. You can just leave it as is. So under here, we see under linear elastic material, it assumes it's a linearly elastic material. You can also assume it's incompressible. You can also make it anisotropic, but for in our case, we'll be assuming it's isotropic. And here you see the materials that it's using. If you want to know the equation that it's solving, you hit equation and there's the set of equations. Now it also, for the boundaries, it assumes that boundary 1 is axisymmetric. It assumes that boundaries 2 and 3 here are free, meaning there's no stresses on it, and you can also indicate initial values for the body of it, either displacement or time dependent, or initial time. Alright, so under mesh, I'm going to choose a little bit finer mesh. You can hit build all if you like to see it. And under the study of eigenfrequency, I like to find the first, let's say 30 eigenfrequencies, and you can tell it to start looking at around 1000 hertz. Alright, you right click and you hit compute. Okay, so that was pretty fast, and you see here that immediately it moves into the result node. So we see here the mode shape solid, which is a 2D representation indicated here on the graphics window, or you can also view it in a 3D mode here. So we see the first under eigenfrequency, you left click on it and you see a list of the eigenfrequencies that it's solved for. The first one being having an imaginary part to it. Now that's a numerical issue, so essentially this is an eigenfrequency of 0, and we see here that the solid black lines represent the original position of your sphere, and we see that the sphere has displaced. So it's this eigenmode is a total displacement, translational motion of your sphere. Now if we click the first eigenfrequency, the second eigenfrequency, I'm sorry, we can see now the actual deformation of our sphere. So on the right hand side you see a scale, color scale, red indicating the most drastic change, blue indicating the least drastic. And just going through a few more, you can see the different eigenmodes of your spheres. Now, having analytically solved for this, the first radial eigenfrequency will be at 3987.9 hertz, and you plot that, and you can see a nice breathing mode of your sphere. Now, one thing to note is, although the scale here you see on the units of above are in meters, this does not mean that your sphere is actually having a displacement of 1.5 meters. It's just an arbitrary unit set. Since we never actually set boundary loads, these are just arbitrary units. So you don't have to worry that it's a miscalculation. These are just meant to help you visualize how it displaces. So look a few more, and you can see how pretty cool it can help you visualize it. So there you go.